Hello, I'm Muhammad Anwar Alhaq, and today I'm going to do a webinar on deep learning based single shot vehicle detection and ego lane detection architecture for forward collision warning system. So before we begin with going into the details of the webinar, let's talk a little bit about the background of the project. So Advanced Driver Assistant System, or short form ADAS, is basically an electronic system that is placed in a car that helps make driving experience more safer and generally more intended into making roads safer. So as you can see here, these are a couple of ADAS application in a car, and as you can see, there are also different types of sensor that is being used for the ADAS application. So as you can see, you have the IR camera, and then you have ultrasonics. So so when it comes to ADAS, uh, so policymakers such as the Euro NCAP and then the NHTSA, and then for the Asia you have the Asian NCAP. So this body usually create create a safety standard uh, for car manufacturers to follow in order for them to be able to market their products to to countries, right? So so basically so basically you have manufacturers that are pressured to do to keep on working on other system to make the car more safer for the user to drive. So let's look into the market scale of automotive imaging. So as you can see here, so the compound annual growth rate uh, is projected to increase by double of what is already in 2018. So you can see that uh, so the field is growing when it comes to camera, and this is for many factors, mainly because camera camera hardware has increased in maturity, and prices are getting uh, cheaper, and the number of applications that you can use using a camera is a lot, and it deems very useful for uh, multiple application. All right, so here you can see the revenue keeps going up as year goes by. So uh, others uh, using vision-based algorithm has many areas that you can touch on. So you have the LDWS, which is Lane Departure Warning System, FCWS, AVM, and traffic sign control recognition. Of course, there's other more like blind spot, etc., etc. But we're going to focus on the our project. My project focuses on the FCWS. So okay, a little bit of statistics. So according to National Highway Traffic Safety Administration of the U.S., it uh, it shows that 80% of all types of accident involve, driver being fatigued and driver being drowsy. So and it contributes 93% of all rear collision. So this brings the motivation why we're using why we're focusing on FCWS. So here, as you can see, we have the mobile eye. So this is one of the model, one of the product out there that uses vision-based detection for FCWS application. So basically what FCWS does is that it detects the object. In our case, it's the vehicle that is in front of the user's car. So it detects the car and calculate the time to collision, uh, of the current car, of the user's car and the car in front of him. So it uses some sort of algorithm that are proprietary to them to calculate the time to collision of the car. All right. So here, as you can see, are some. So here on the left, you can see some of the some of the algorithm that comprises FCWS. All right. So basically, two main components here, which is the first of all the car detection, of course. Secondly, we have a second type of detection, which is the lane detection. So lane detection is important here because in order for the algorithm to discriminate between what vehicle is in front of you and what is not you, one way of doing it uh, is for the system to understand what is your ego lane. So when you know what your ego lane is, you will be able to discriminate what is not in front of you and what is not in front of you. Okay, so a little bit of literature, a little bit of background on traditional methodology on object detection. So here we'll look into how traditionally vision-based detection is formed. So, uh, so basically, say you have an image. So next step will be to extract features out of it. So extracting features traditionally are usually hand features, meaning you have to come up with your own kernel. You have to, you have to come up with your feature extraction method, which is hand features, hand featured by the designer himself. So, so yeah, so once you extract feature out of it, you uh, you you feed it to a trainable classifier, so the whole system can tell if, in this case, if what you're looking at is a car or if it's not. But of course, you can also, cascade multiple feature layers, right? All right, and then use that final feature layers to train classifiers. All right, here are some examples. So you have the hard cascade classifier. So, just basically use a sliding windows method, and then based on the feature learned by the other boost algorithm, it sees if it's actually detecting a face and an eye or not. So histogram of gradient uses feature extraction method of by using histogram of gradients. Yeah. So it takes gradients of an image and then create a histogram of different type of the histogram that is available. Okay. So these are some of the examples using traditional method of uh, detecting images. Traditional method of detecting lanes are using a very well-known image operation, right? So like perspective warp, color filtering using the HSV. So in this image, you can see you can see color filtering here, right? So it's so it tries to filter out everything, tries to filter out that is not white, and then make a binary image. And then here, clearing all the noises, uh, and then uh, allowing you to be able to create to filter only the lane lines here. So let's take an example here. I mean, so here on the left you have the row image of the uh, road with the lane. So by doing some perspective transform, you can isolate it to only look at the lower part of the road, and thus allows you to do color extraction, and then do some, I don't know, polynomial fitting to give more confidence to what is lane and what is not, and then do an inverse perspective transform back into the original image, and then creating a line detection. So you've seen the two detection methods for two different area of, first detecting an object and then detecting lanes, right? So the issue with the traditional method is that you need to have two separate algorithms to run to build up an FCWS system. So what our architecture proposing is a unified architecture that tells us vehicle location and the lane location on an image one shot at the same time, like simultaneously. The architecture is real time, has a practical use for FCWS, and it's scalable for all types of detection. So this is our architecture proposal. And here, yeah, so in order to do this, we use a deep learning approach. So what makes it different? What makes deep learning different from the traditional method of detection? So here in detection model, I mean using deep learning, you have bunch of layers, convolutional layers that extract features. So here you see a lot of layers. See a lot of layers. These are convolutional layers. So these are responsible of extracting features from the layer before it. So in this case, the first layer is our image. So it extracts and gives out low features level, and then max pooled it, or max pooled it, and then making it an output for an input for this layers, and then I mean it keeps on cascading, and then finally it's squeezed small enough that it gives you feature vectors, a final feature vector, so that this feature vector can tell you if it actually sees in this case a car or not. Okay, and yeah, and this is and deep learning is mainly, and this is learned, and this has nothing to do with traditional way of hand featuring stuff. So what you do in deep learning is you construct the architecture, and then use a learning algorithm to train it to detect whatever you want it to detect, right? So that's one of the advantages of deep learning, is that the method of creating the architecture and then using a learning algorithm to let it learn to classify things on an image. And so that gives you an idea that this is already scalable. So this doesn't only work for car; it can work for any other kind of classification task as well. So yeah. So an overview of our system, our proposed system, is so this is the single shot system for car detection and lane detection. So previously, when I showed you this architecture, so this architecture extract features by the merit of the convolutional layers, right? So this is called the feature extractor architecture. So in order for you to do detection, you need a meta architecture that helps you with giving prediction for the bounding boxes. So as you can see here, so a single image goes into a feature extractor architecture, and then you have a meta architecture that utilizes this feature extractor to output bounding box coordinate of the vehicle. But then at the same time, we have attached a layer that gives you a regression output of where the lanes are. And how is this possible? Okay, first of all, so from literature, there are a couple of meta architecture that you can use for detection, and then you can use. There's more than this feature extractor architecture that you can use to extract features. So let's take an example on this problem. So this is a problem of estimating human pose, to estimate where several joints of your body are. So in this problem, you're able to. So this problem basically is a problem of training a feature extractor architecture to predict the coordinate of each joint. So when you're training, you're actually feeding the image with the labels of what are the coordinates of each joints are. So this is like a regression problem, right? So for the FCWS deep learning based problem, what you can do is have a feature extractor architecture that does regression, that treat the ego lane detection as a regression output. So when you train this architecture, you give labels of where the lanes are in an image, and have that as a label of the image for the trained architecture. So here is how you do pre-processing. So treating an image, okay, so definitely we need to set standards. Set standard for the pre-processing so that it's not messy. So we need to create standard on how the architecture should take in images, and then how to label this thing. So to treat the lane detection problem as a regression problem, first of all, in my case, resize it to the input of your feature extractor architecture. In this case, I chose 224 times 224 for a reason, which I'll tell you in a bit. So resize it to this size, and then uh, take take a coordinate of the lane at every 10 steps, right? So for the left lane and then for the right lane. So that creates you a vector of coordinates for both left lane and the right lane. And then we'll use this resize image to feed the architecture. So the architecture will only learn to give prediction for images that are in this size. So for this project, we proposed the MobileNet feature extractor, and then we have the SSD meta architecture for detection. All right. So we first trained the feature extractor on lane detection. So we trained the deep learning architecture to to predict to detect where the lanes are. Once you do that, you freeze the weights of the feature extractor and then train the mecha architecture to predict bounding box of the car. So yeah, basically that is how you achieve single shot vehicle detection and eagle lane detection using one architecture. So to test, for this project, we trained using this open source lane dataset, and then we have our own Malaysian dataset that we labeled our own. Okay, and of course we have our own Malaysian dataset for car detection, car or vehicle detections in general. And yeah, so this is the output of our own lane detection architecture. So this is the accuracy point using the CU lane dataset, and this is using the only Malaysian dataset. And comparing it to this paper, we achieved 88% among these other architecture for lane detection only. Okay, so yeah, so this is the result for the car detection. Okay, I think it's fairly good. Also, one thing we forgot to show here is also the uh, performance results, which is real time, and it achieves around uh, around 60 FPS on GTX 1080 GPU. So which is fairly real time, and yeah, and it gives single shot vehicle detection and lane detection. Okay, I guess that's it for the webinar. Thank you very much.